We'll get started in just a second. So I put back up on the whiteboard the diagram that I made the other day that was virtually invisible to everybody online. So the idea is that if we think about, for example, hydrogen, an amide hydrogen that is bonded to an amide nitrogen, it's an N15, then because the N15 is spin 1/2, the N15 spins are either in the alpha or beta state. And because the population differences are small, there's essentially half of the nitrogens in the alpha state and half the nitrogens in the beta state, which means that half of our proton magnetization is connected to a nitrogen in the alpha state, and half our proton magnetization is connected to a nitrogen in the beta state. So I've indicated that here with the proton magnetization, Z magnetization connected to the beta nitrogen in orange, and the proton Z magnetization connected to a nitrogen in the alpha state in green. And the total magnetization is just the sum of those two. But if I apply a 90-degree pulse on the protons, say a 90-degree Y pulse, then both of those components get rotated to the x-axis. If it's an ideal 90-degree rotation, my thumb on Y, my fingers go towards plus X. So they're oriented in the same sense, which we would call being in phase with respect to each other. And if I turn on the receiver, I'm going to see the usual in-phase doublet that you're used to seeing, in which the two lines are separated by 2 pi j in angular units or j in frequency units. And that means relative to the chemical shift of the I spin, one doublet component has a frequency upshifted by pi j, and the other doublet component is downshifted by pi j. This all depends on, of course, the sign of j, so these can swap around, but that doesn't affect the argument that I want to make. But then, if instead of turning on the receiver, we sat on resonance with the I spin, so that there was no chemical shift precession, then we would just see evolution due to the J's. So what's shown here, then, if I wait for a time period 1/2J, then the proton magnetization that's connected to the S alpha nitrogens has a frequency of pi j. And if I rotate by a time, 1/2J, frequency times time is an angle. So pi j times 1/2J is pi/2. I get a rotation by 90 degrees. And the green vector rotates from x to plus y. 90-degree rotation with my thumb on Z. Whereas the magnetization connected to the nitrogens that are beta rotates by minus 90 degrees and ends up on the minus y-axis. And at that point, if I turn on the receiver, this is what we talked about the other day, I'll see what we call an antiphase doublet. The two magnetizations are 90 degrees or 180 degrees out of phase. And then one doublet component is positive and the other doublet component is negative. Now, in fact, if I had phased these to be absorptive lines so that they have, the normal absorptive line shape, these lines would be dispersive then they would look more like that. But then I just on the spectrometer apply a 90-degree phase shift and make them look absorptive again. So that part's trivial. So this is what we did before, just to show how this works. And here, then, as I said, my language says I can define a new operator because the total coherence here is IY S alpha minus S beta. And in my symbol world, 1/2 S alpha minus S beta is SZ magnetization. So if I divide by 1/2 and multiply by 1/2, I call this then 2 IY SZ. And you get used to these factors of 1/2. And now, this is where we kind of ended this discussion last time. And now, suppose I apply a 90-degree X pulse at this point on the I spins. A 90-degree X pulse takes Y to plus Z. So after a 90-degree X pulse, right, this one rotates up, this one rotates down, and I have now the green vector is up and the orange vector is down. And my operator then turns into 2IZ SZ. I applied the 90 rotation only to the Y spin, so the S spin just stayed where it was. And ew, this thing is leaking. We're done with the orange. This is called longitudinal two-spin order. Longitudinal meaning there's only Z operators and two-spin being obvious. So then you might notice that this is completely symmetric in I and S. It's SZ and IZ. And because of that, there's nothing stopping me from now applying a 90-degree S pulse, say with X phase. And when I do that, I'm going to have 2IZ SY with a minus sign. And now my thumb is on X, my fingers are on Z, I rotate to minus Y, but I'm doing this on the S spin, leaving the I spin alone. But if I turn the receiver on here, what spectrum will I see? There's my frequency axis. What am I going to see? It's going to be an antiphase doublet. And what frequency will it be centered on? The S spin frequency, not the I spin frequency, because the transverse operator is the S spin. So I'm going to see, and because of this minus sign, it will be opposite from what I had before. So it's going to look like this. But the key thing is the antiphase doublet is on the S spin. this is what we call coherence transfer. I transferred magnetization from the I spin, where I had the I spin antiphase doublet, to now the S spin, where I have the antiphase doublet. And that happened because I went through the symmetric state. And the symmetric state then doesn't care whether I got there from the I spin or got there from the S spin. I can come out of this state either back on the I spin or on the S spin. And while in some experiments, it's not so obvious that this is happening, but anytime there's coherence transfer from one spin to another, it invariably has to happen through some symmetric state, even though that in this particular case, it's easy for me to see the creation of the symmetric state. In other cases, particularly homonuclear experiments, that state is kind of created during the pulse and then disappears. But kind of conceptually, magnetization transfer of coherence from one coherence to the other almost invariably has to go through some kind of symmetric state. You also might have known, yes, that a state like this had to exist, the symmetric state, because for our two-spin system, there's 4 diagonal elements, right? Our operator matrix is 4 by 4. So there's 4 diagonal elements. And obviously the identity operator is the diagonal matrix, the identity matrix. And then we saw the IZ magnetization is the sum of 2 of the states where the I spin is alpha minus the 2 states where the I spin is beta. And then the S spin magnetization was another combination. But if we have 4 diagonal elements, there must be 4 independent linear combinations of those diagonal elements. And the 4th one is this. And you can then work out what this looks like as a matrix. Okay, so if I switch this to a different representation, this is 2 times 1/2 I alpha minus I beta times 1/2 S alpha minus S beta. And if I multiply this all out, it's 1/2 that I don't really care about. I alpha S alpha minus I alpha S beta minus I beta S alpha plus I beta S beta. And in my matrix, this is the diagonal 1 minus 1 minus 1, 1. So the difference in populations between the double quantum states minus the populations of the 0 quantum states is what we call 2-spin order. But there had to be a 4th one, because you can always, if you have 4 numbers, you can form 4 independent linear combinations. So we knew 3 of them: identity, IZ, SZ, and this is our 4th one. So that's by way of filling in a bit from the other day. Hopefully a little clearer to see for the people online. And now we're ready to walk through the COSY experiment in some detail as the prototypical 2D experiment. Also, can't remember if I told you, the COSY was the first 2D experiment proposed. And to give you some sense of how much the world has changed, back in the mid-70s or so, Jean Genet at a conference presented a theoretical analysis of this 2-pulse experiment in a 2D format and never published a paper on it. And postdocs of Richard Ernst at the meeting went back to the lab and said, we just heard this fantastic talk about this new invention of 2D NMR. Of course, today, no one would have a groundbreaking discovery and just mention it at a meeting and never publish a paper about it. Okay, so we've done the Gedanken experiment, and the problem with the Gedanken experiment was that we had to apply a selective pulse to get the experiment started. And you'll see this. I mean, there are real experiments called soft COSY, in which you start with a selective pulse or a band selective pulse. But the conventional experiment, we want to start with a hard pulse. We want to be non-selective because that's obviously easiest for crowded spectra. So here's the sequence. And we assume we start with Z magnetization. And again, I'm just going to work it out for spin 1. I'm going to assume I have homonuclear spin system, and I'll call one proton I1 and the other proton I2. Sometimes I switch back and forth to I and S, but here we'll call them I1 and I2. And I'm only going to just pretend that I'm starting with I1, even though it's a non-selective pulse, just to save writing. And at the end, I can figure out what happened to spin I2 just by swapping all the labels, since it's non-selective pulses on the homonuclear spin system. Otherwise, I have a lot more writing to do, and it just doesn't fit on the slides. So we start by applying a 90-degree pulse, and by now it ought to be second nature that IZ turns into minus IY. And now, during the period T1, which is going to be a variable time, but for any one acquisition, it's fixed. During T1, the magnetization is going to evolve under the chemical shift and the scalar couplings. So it doesn't matter which order I do it because we're in the weak coupling limit. So I'll do the chemical shift first. So omega 1 is the chemical shift of spin 1. And minus IY cosine omega 1 T1 plus I1X sine omega 1 T1. And again, for shift precession is shown here. My thumb is along Z. My fingers start on minus IY and then rotate towards plus IX. And then I do the scalar coupling. So each of these two terms splits into two more terms. And here, for example, is the picture that I would draw for IY evolving under the scalar coupling. So I have IZ, IX, IY, and then because I'm interested in how IY evolves, I decorate the IZ axis with 2SZ and the IX axis with 2SZ, so that IY under the J coupling evolves into 2 minus 2IXSZ. Everybody happy with that? IY will rotate towards the back here and give minus 2IXSZ. And then there's another picture for the evolution of the IX term. That picture is shown here. IX will evolve to give 2IYSZ. You can see the patterns. The transverse operator evolves just in a kind of normal right-handed sense. Under the scalar coupling, you pick up the SZ component or lose the SZ component of the coupling partner. So here are the four terms we end up with. And again, since most experiments start with some Z magnetization followed by a time delay, this kind of pattern is something you'll see all the time. Of course, we've limited ourselves to just two spins here, but if the I spin was coupled to a third spin, I3, then we would now apply the I13 coupling and evolve all of these terms again under that coupling. So we would end up with 8 terms to keep track of. And shortly after that, we give up and let a computer do the calculation. And now comes the important part. In our, by the way, the 2D experiments are usually conceptualized in this block structure. So there's a period called the preparation, where we start with the equilibrium density operator and turn it in to the desired operator. In this particular case, all we did was apply a 90-degree pulse. So the 90-degree pulse is the preparation period. But in other experiments, the preparation period might be a series of pulses and delays. And probably everybody in the room has seen HSQC pulse sequence. And in that case, the preparation period is a series of pulses and delays that we call an inept sequence to generate an operator that depends on, say, the X frequency, the nitrogen frequency, or the carbon frequency. So the preparation period could be complicated. Then there's an evolution period, T1, where that whatever operators we produced after the preparation period then evolve under the chemical shift and scalar coupling interactions. In this particular case, it's just free precession. But of course, we might have pulses in the T1 period in order to modify the evolution. And most commonly, we might apply pulses to decouple some of the J coupling interactions. And then mixing, again, in this sequence, what happened to my cursor? There we go. In this sequence, the mixing period, again, is going to be a single pulse, the second 90-degree pulse. But in other pulse sequences, again, that could be a series of pulses and delays. And mixing is going to transfer coherence from whatever our operators were at the end of T1 to new operators whose frequencies or evolution we're going to record during acquisition when we actually record a free induction decay. So here is the mixing pulse, and I've taken it to be another X pulse. You can see I have them designated phi1 and phi2 because I might change their frequencies during the experiment, but for right now, we're just calling them phi1 is X, phi2 is X. And then I just work my way through term by term. In this case, the pulse is non-selective, so I have to rotate both the I1 operators and the I2 operators. And I know, for example, here that minus IY magnetization rotates towards minus IZ magnetization. So I've done that with this first term. Minus IY became minus I1Z. And all the trig coefficients, those are just numbers, so they just come along. And then here, IX, IZ nothing happens to the X operator, and the IZ will get rotated to minus IY, and here we have it. I1X, I2Y, the minus sign, and the trig functions just come along. So I rotate all four terms. And now they're going to evolve during acquisition, and I want to pick out what the spectrum looks like. Now, last time we realized that we don't have to actually do the evolution. We can figure out what the spectrum looks like by inspection of the operators. So here, during acquisition, right after this pulse, we turn on the receiver and record the free induction decay. So during T2, how will I1Z evolve?
Goes to the positive.
Well, it'll relax back to Boltzmann equilibrium, but if we ignore relaxation now, nothing happens, right? Z magnetization commutes with the Hamiltonian for chemical shift and for scalar coupling, because those are rotations around Z, and rotations around Z don't affect the Z operator. So nothing happens here. And then we have this, an operator with two transverse components. So that's a mixture of single and double quantum coherence. And that will have zero trace with the detection operator.
Zero and double.
What did I say?
Single and double.
Oh, zero and double quantum. And that will have zero trace with the detection operator. And it doesn't evolve under the J coupling into anything else. We talked the other day about the fact that the J coupling just moves the double quantum levels up by the same amount and moves the zero quantum levels down by the same amount, so that the zero and double quantum coherences aren't affected by the J coupling. So that operator can only evolve under the chemical shifts of the two spins, but will never have a non-zero trace with the detection operator, because the detection operator, as we saw, only has a non-zero trace with operators proportional to I minus, or I1 minus, or I2 minus. So the first two terms don't give any signal. The third term is IX. That certainly will have a non-zero trace with the detection operator, because IX is the sum of I minus and I plus. The I plus won't have a trace, but I minus will. So this will generate a signal during the acquisition period. It's on the I1 spin, so the frequency will be omega 1, the chemical shift of the I1 spin. Is it going to be an in-phase or antiphase doublet? In-phase doublet, because we have to imagine that it has the identity operator for the S spin there, and the identity operator for the S spin is S alpha plus S beta. So both multiplet components have the same sign. So that will be an in-phase doublet at the omega I frequency. And then over here, what do we have? First, what's the chemical shift frequency? It's going to be at omega 2, because the transverse operator is on the spin 2. And is it in phase or antiphase doublet? going to be antiphase because IZ we could write as 1/2 S alpha minus S beta. So one of the lines is up and the other line is down. So by inspection, we know that during detection, we're going to have an in-phase doublet at frequency omega 1 and an antiphase doublet at frequency omega 2. This is super important that you see this. So if there are questions online about this, chip in.
I just want to ask here that the second term would generate an antiphase doublet at omega 2.
Mm-hmm.
And then there is also the magnetization which came from equilibrium I2 for the Z.
Right. So then for that, we're going to, if we added in the other spin, we're going to have, if I just swap the labels, we will have an in-phase doublet at omega 2 and an antiphase doublet at omega 1.
Yeah.
Mm-hmm. By just swapping all the labels. The other question before we go on are what are the relative phases of the signals? Remember, we pick out the I minus part. So our IX operator is 1/2 of I plus I minus. Nothing special. Our signal, right, is just proportional to I minus and a trivial factor of 1/2. But what about IY? IY is 1/2I, I plus minus I minus, and minus 1 divided by I is equal to I. So we could write that signal as I times I minus. And I is, that factor of I means that the signal is 90 degrees out of phase relative to the IX signal. Another way of seeing that, if you remember Euler's rule, e to the I theta is cosine theta plus I sine theta. So I is equal to e to the I pi over 2. And I pi over 2 is a phase shift. So whenever we see here that we have transverse signals where one is IX and the other is IY, those signals are going to be 90 degrees out of phase when we Fourier transform the data. Now we can always rotate the phase. So we could decide, normally I will say that IX means an absorptive signal, an absorptive line shape, and IY means a dispersive line shape. And you'll see more about what those look like shortly. I'll refresh your memory as to what they look like. But that's arbitrary. I can always apply a 90-degree phase correction, in which case IY turns into the absorptive line and IX becomes the dispersive line. In this particular case, right, all I have to do is multiply the signals by minus I, and the I turns into a 1, and the X turns into a minus I, or that's the same on the computer as swapping real and imaginary parts of the numbers and negating one of them. So actually on a modern spectrometer, when you apply a 90-degree phase shift, there's no phase calculated. The spectrometer just swaps real and imaginary parts and negates one of them. It's a lot faster than actually calculating a complex exponential. So we can inspect the operators and decide what generates an observable signal during T1, what generates what the line shapes are and what the multiplet structure is just by inspection. And that's also a great part of the symbolic language, because actually calculating the evolution during T2 and then taking the trace with the detection operator, that's a lot of work, and we don't have to do it. Now, a critical thing here is, suppose there wasn't a J coupling between spin 1 or spin 2, so that J12 was 0, then our second observable term would vanish, because sine 0 is 0. So the J coupling needs to be non-zero to see this antiphase term. And the antiphase term is the coherence transfer. We started on the I spin, we ended up on the S spin. The appearance of the antiphase operator is a sign that the coupling is non-zero. And that's the critical part of the experiment, is identifying the coupling network in the molecule. On the other hand, the J coupling, it's not enough that it be non-zero, it has to be resolved relative to the relaxation rates. Because of course, what's really happening is we're building up that antiphase term by a sinusoidal function, but our signal is decaying away with some relaxation rate constant. So these are competing processes, and you can see what happens here. If there's no relaxation, I just have the sine curve. I can transfer all the magnetization and set my delay to 1 over 2J, all the coherence is transferred. On the other hand, you can see if R2 gets to be the size of J, then the optimal time for transfer shifts to shorter times, and I can't transfer as much magnetization. Some of it is relaxed away, and that's end of story. And when the relaxation rate, gets to be 10 times the J coupling, right, there's almost no hope. All the signal relaxes away before it can get transferred to the second spin. It turns out, something we'll see in a couple weeks, that R2 in a macromolecule to a first approximation depends on the tumbling time of the molecule times the variance in the frequencies caused by fluctuating Hamiltonians as the molecule tumbles. And pretty much everything about modern NMR is in these two equations, because 2D NMR and structure determination by NMR started with only proton experiments. So the proton couplings, big ones are 12 to 15 hertz. So you work on VPTI, the tumbling time. Oh, how does tumbling time depend on size of protein or size of nucleic acid? Pardon? I just didn't hear.
Is it faster when it's small?
Yes. So it's basically roughly proportional to mass, because volume is roughly proportional to mass for a uniform density object. So the protein gets bigger and bigger, nucleic acid gets bigger and bigger, tau C gets larger. And so experiments that work fine on BPTI at 58 residues or so, amino acid residues, start to get really difficult when you get to 10 kilodaltons of protein. And then that's when we switch, fortunately about that time, when all the small proteins had their structures done. Fortunately, about that time, it became straightforward to incorporate carbon-13 and nitrogen-15 into proteins, and then eventually into RNA. And now the amide hydrogen to nitrogen scalar coupling in a protein is 93 hertz. So rather than being down here with the proton couplings, suddenly you're back up here somewhere, and experiments all work great. And then your boss keeps wanting you to work on bigger and bigger proteins. And when you get to 30 or 50 kilodaltons, you're back down here somewhere where the experiments are getting really difficult to do. But there aren't any bigger J couplings. We've run out of J couplings. The only other important part in the equation is R2, and R2 basically has two components. So you can either make tau C smaller, or you can make that variance smaller. So how do you make tau C smaller? What are your options?
Immobilize the protein.
Pardon?
Immobilize the protein.
Immobilizing makes it go even slower.
Right.
And you can switch the solid state NMR, of course, but then you have to spin really fast by MAS to replace the fact that there's no tumbling. Right? Somehow you have to make the protein the molecule tumble faster. So what are your options?
Probably using phase separation, like the boundary between two phases of the nucleus.
Yes, so that's basically what Josh Wand
Yeah.
invented. So you have the protein in a reverse micelle. So the protein is surrounded by water, but the outside of the micelle is hydrocarbon tails. So you can put it in liquid ethane under pressure. And even though you have a big particle, the viscosity of liquid ethane is so low that the big particle tumbles fast enough to see narrow lines for the encapsulated protein. It's a brilliant idea, but it's hard to get your arbitrary protein encapsulated into a reverse micelle. So it's not really taken over, even though it's a super cool idea. And actually, when I switched from doing fluorescence to NMR, the first time I saw my thesis advisor at a biophysical society meeting, she said, "What have you learned about NMR so far?" And I said, "I've learned it's mostly a drag because the molecules tumble too slowly." And she said, "You have to figure out a way to make them tumble faster." And I should have listened to her. She said the right thing. But if you don't do Josh's trick, what can you do?
Increase the temperature.
You increase the temperature. Of course, your boss wants you to work on some delicate human cancer-causing protein that falls apart with the raise of the temperature. So what you go and find the hyperthermophilic counterpart, raise of the temperature to 45 degrees, right? And then try to extrapolate back to the human protein, right? And this is done all the time, not just by NMR spectroscopists, but all biophysicists play this particular trick. All right, what else can you do? I mean, the RNA people do this all the time. I mean, you have your 300 nucleotide RNA packaging signal or something. You put all 300 nucleotides into the NMR machine.
Cropping.
You find domains where you think I can work on the domains, and then I try to stitch them together in some way to get a full picture, maybe doing scattering or something else to try to get a picture of what the intact molecule does. Proteins, we do the same thing. You do a sequence analysis, find out what the domains look like, clone out those domains, right? Divide and conquer and try to build things up. But as far as we know, as far as I know anyway, those are the only three things you can do with temperature. You can try to lower the viscosity, you can raise the temperature, or you can actually work on a smaller molecule. If you think of a fourth way, you'll be really famous as a grad student or postdoc. And then your only choice is how to make the variance in these fluctuating fields smaller. And the dominant fluctuating field for proteins we'll eventually see is coming from dipole-dipole interactions and chemical shift anisotropy. If we ignore deuterium, where the quadrupole interaction is dominant, but for the spin 1/2 particles, dipole-dipole interactions and chemical shift anisotropy are the two dominant effects. So if we want to make the variance smaller in the fluctuating fields, we have to attack those two interactions. So what do people do? So TROSY is a way in which you make the variance smaller by correlating fluctuations that go in one direction for one interaction and the other direction for the other, so that their sum is a small fluctuation. What else might you do? What's the biggest dipole-dipole interaction, the strongest dipole? Proton-proton. You deuterate to reduce the number of proton-deuteron interactions. And for proteins, it's common, deuterate the carbon-attached hydrogens and then soak back in water to get the amide hydrogens back to be hydrogens rather than deuterons. And at this point, those are mostly the two tricks. And if you invent another trick for narrowing that variance, you get to be very famous NMR spectroscopist. But it's sort of, to me, pretty remarkable that these two short equations are basically most of the box as to whether an NMR experiment is going to work. Now, if we come back here for a moment. Oh, the other thing I say, these equations are short. So of course, if you're in need of more tattoos, you can fit these tattoos one on each arm, so you never forget these equations. Now, we have the problem here, right? So when I add in the other two components that started on the I2 spin, we're going to have our in-phase multiplets have the same shift as our antiphase multiplets. And we're only interested in the antiphase multiplets. They tell us if there was J coupling. So to separate them, we're going to vary T1. Because if we think about my cursor here again. So for example, here, there's going to be an in-phase multiplet at the I2 omega-2 frequency that came from the other partner that I didn't write down. But its modulation is going to be omega-2 T1 because it'll have started on the I2 spin. So during T1, that operator will evolve at the frequency omega-2. So assuming omega-1 and omega-2 are different, they're going to have different time dependencies on the variable T1. So as we change T1 and record different signals, our detected signals are going to be modulated in some way by the frequencies that evolved during the T1 period. So we can separate then the in-phase operator from the antiphase operator by their different dependencies on T1. And you would think what we could do, is just pick a few values of T1 and do some kind of least squares fitting of the sinusoids. And that turns out to be pretty inconvenient. Fitting sinusoids is difficult because you can easily fit harmonics of them. But you could say, I have some functions of sinusoids and I want to resolve them. You could think of lots of ways of doing it these days. We're going to do it by Fourier transform, but Fourier transform has limitations. In particular, that we have to sample T1 at constant intervals. And now, of course, there's lots of ways to get around that restriction that people call non-uniform sampling. And before long, it'll just be an AI program that'll do this for you. So the main point is that our different signals have different sinusoidal dependencies during T1, and that lets us resolve them in a second frequency dimension. And how we do that mathematically isn't so important. We'll present it as a Fourier transform. That's convenient because we Fourier transform during acquisition anyhow, so we know how to do it. But it's not essential. Any data analysis approach that could separate time-dependent sinusoids and resolve their frequencies as good as any other. So here's the idea. We're going to start those two pulses close together. T1 will be 0. We'll only see the cosine term because cosine of 0 is 1. And then we move them up and we'll record some spectrum. We move them a little bit apart. We record a spectrum, and the amplitude and or phase of the spectrum is going to change because of evolution during the T1 period. And then we move the pulses a little further apart. We record another spectrum, so on and so forth. For each real spectrum we record in T2, we do the Fourier transform. So we have a spectrum as a function of our real acquisition period. And the appearance of that spectrum, as you can see, is modulated by whatever happened during the T1 period as the pulses got further and further apart. So again, this change in amplitude or phase is what we want to analyze to resolve the different components in our density operator. And what we will do for the purpose of much of the course is say, we just stack these up in another dimension, pick columns and do a Fourier transform column by column, and end up then with a two-dimensional spectrum in which the peaks that came from operators that had the same frequency in T1 that they had in T2 will lie on a diagonal, and operators that had different frequencies in T1 versus T2 will be off the diagonal somewhere. And if we go back up here, we can see here, this operator has a frequency omega 1 during T2, and it had a frequency omega 1 during T1. So it's going to be on the diagonal. Whereas this operator had a frequency omega 1 during T1, but it's going to have a frequency omega 2 during T2. So it's going to be off the diagonal. And then the other pair will be just the opposite. We'll have an operator that had a frequency omega-2 during T1 and a frequency omega-2 during T2. It'll also be on the diagonal. And there'll be an operator that had a frequency omega-2 during T1, but has a frequency omega-1 during T2. And that will be another cross peak off diagonal. And that's shown schematically here. And the most important thing is the appearance of the cross peak. The cross peaks can only arise if the J coupling was resolved. Otherwise, we would just see diagonal peaks. So this is, of course, you could wonder exactly what happens here with these trig functions when we Fourier transform them. So that's just worked out here. If I take something like sine omega T1, cosine pi j T1, one of those trig terms that came from evolution during T1, if I want to know what it looks like after I Fourier transform it, one way is to just write it out as complex exponentials, because every complex exponential is going to be a frequency after we Fourier transform. So if I just write everything in complex exponentials using Euler's law and multiply them all together, then I end up with a term that's positive omega-1 minus the J coupling and positive omega-1 plus the J coupling. So that's a doublet at the frequency omega-1. And you can see I also get a doublet that is upside down, but the frequencies are inverted. You don't normally see that, right? That's because this, well, you can see it. This comes, so, and if I do another one, say sine, you can see the main difference is going to be I have antiphase doublets rather than in-phase doublets. So first of all, I have the rule that if the J coupling is cosine modulated, that's going to lead to an in-phase doublet after Fourier transform. Cosine is the sum of two complex exponentials. If I have a sine modulation of the coupling, that's going to generate an antiphase signal after Fourier transformation. When I then have the problem that I have two doublets when I expect one doublet. And that comes from the fact that I've only measured the sine component of the evolution under the chemical shift. And the sine or the cosine, right, they're both sums of complex exponentials. I only want one complex exponential. So to resolve this, I need a second experiment where I measure the cosine of the chemical shift evolution rather than the sine. And this is called frequency discrimination. And it can be done in multiple ways, but here I did it in the way that's probably most common. So I changed, actually, I didn't do it in the way that's most common. The cursor, there we go. So here I changed the phase of the second pulse to be Y rather than X. Most of the time, if you looked in the pulse sequence, you would see actually was the first pulse the pulse before T1 that was changed. And that's really for some experimental reasons rather than theory reasons. From the theory, it doesn't matter. I just need to change one pulse, the pulses relative to each other by 90 degrees. But when I do this and change the phase, now you can see these are the operators I don't detect. And now these are the operators I do detect. And this one is now cosine modulated with respect to the chemical shift rather than sine modulated with respect to the chemical shift. It has the same dependence on the scalar coupling. Similarly, this one is cosine modulated, but has the same dependence on the chemical shift. So then I have my two data sets, and I can add them up in such a way to generate only a single frequency that cancel out the image frequency that came from having only one component. So that's shown here pictorially. I have in one modulation, if I have the cosine modulation of the chemical shift, I have two positive frequencies, one at plus omega and one at minus omega. If I have the sine modulation, I have one positive and one negative because sine is the difference in two complex exponentials. And then I add them together and one lobe cancels. And I just see a single chemical shift frequency. This doesn't come up in acquisition because during acquisition, the spectrometer is designed to measure both the X and Y projection of the precessing magnetization. I don't think there's anybody left here who's ever tuned the timing belt on an automobile, but it's a classic problem if you have a wheel going around and you want to measure its frequency, right? A classical way is to put a white paint spot on the wheel, and now the spot is whizzing around, and now you adjust a strobe light that flashes at a known rate, and when the light is flashing at the same rate as the wheel rotating, right, the spot appears stationary. You have no experience doing this in a car. You might have some experience with this in a disco. The problem, if you only have one spot, is you can't tell whether the wheel's going this way or that way. To tell which direction the wheel is rotating, you have to have two spots 90 degrees apart from each other. And that's called quadrature detection, because you're measuring in quadrature to tell the direction of rotation of a shaft, of an axle. And so this is called quadrature detection in NMR for the same reason. We want to know whether the magnetization is precessing clockwise or counterclockwise during T1. We can usually only measure one component at a time, either the cosine component or the sine component. And therefore, we need two experiments in which we measure sine in one and cosine in the other, and then manipulate them to give us the right sense. Of course, you may notice sometimes when you're calculating two-dimensional spectra or three-dimensional spectra, sometimes you'll notice that the spectrum looks upside down relative to what you expected. And that just means that this addition process happened incorrectly, so that you ended up with the other component rather than one you wanted. And this depends on the nature of the pulse sequence, et cetera. One can always calculate it, but usually when the spectrum looks upside down, and then usually you take the complex conjugate and it flips around. There are spectra in which it's hard to know just from the appearance of the spectrum whether it's flipped or not. Carbonyl spectra, for example, don't have the same kind of obvious upside downness as a nitrogen HSQC or say a carbon HSQC. And so if you need to know, you have to make sure all of your frequencies are either positive or negative, which means you have to take a trial spectrum with the RF carrier on one side or the other of the spectrum, right? Normally you put the carrier in the middle and then you have to know which side is positive and which side is negative. But in a trial spectrum, if you put the carrier where you know you're on one edge, then you know I should see the frequencies all positive or the frequencies all negative. Once you figure that out, you can put the carrier back in the middle. Yeah, we once deposited a carbonyl spectrum upside down and then had to correct it. Here's absorptive versus dispersive line shapes in 2 dimensions. Again, depending on the phasing, the phase cycle, etc. Some pulse sequence you run can give you the wrong phases, and then you usually have to go back and fix the phase cycle. Anyhow, I did another simulation. I think maybe the Python code isn't in the Dropbox yet. I'll add the Python code in if you want to fiddle around with Python and simulate spectra. But here are different free induction decays. Here's the result. You'll notice that the diagonal peaks and the cross peaks are out of phase. Right? We worked out that one was dispersive and the other was absorptive. And it's up to us which one to make absorptive and which to make dispersive. We care mostly about the cross peaks. So in this experiment, cross peaks are usually phased to be absorptive. So we have nice line shapes, and that makes the diagonals dispersive. And you have these dispersive tails coming off the diagonal. That makes it hard to see cross peaks that are very close to the diagonal. And lots of graduate student lives have been spent trying to develop pulse sequences that get rid of the diagonal dispersive tails in a cozy spectrum. Here's what it looks like for ubiquitin. You can kind of see up here by the methyls some of the dispersive tails coming off of the methyls and how hard it'll be to look at peaks that are close to the diagonal. On the other hand, over here, the amide alpha cross peaks are well resolved from the diagonal. So this tends to be, for lots of cozy spectra, kind of the most important region, because you should have a cross peak for every non-prolyl amino acid other than the N-terminus. So it's easy to go count. So for proton-proton experiments, this is kind of the corollary to the HSQC, where you run an HSQC and immediately count, do I have the right number of peaks? And if you have way too many, you have a problem. And if you have way too few, you have a problem. Similarly here, you count up, you know how many you should have. So it's a quick diagnostic. If we zoom in, you can kind of see most of the spectra I'll show you. A contour with a single line is a negative peak, and contours with multiple lines are positive peaks. And you can see, just as our operators predicted, the cross peaks are antiphase in both dimensions. We had antiphase operators during T2, and they had a sign modulation with respect to the J coupling during T1. So we know they're going to be antiphase in T1. When you have more than one coupling partner like glycines, you start to get more complicated coupling patterns. because multiple couplings are evolving. And back when these kind of homonuclear experiments were all that existed, there are papers, tabulating all the different coupling patterns you expect to get for the amino acids and for the sugars and bases in nucleic acids, so that looking at the fine structure of the coupling could help resolve ambiguities as to what amino acids you were looking at. The square boxes shown here are peaks that are missing, that from other experiments we know are there. And they're missing because this experiment obviously is done in water. There has to be some water suppression, and those particular residues exchange fast enough with water to be bleached out in the experiment. One has to do other experiments to find them. And that's also a common issue in hydrogen homonuclear experiments. The need to suppress water can result in various artifacts, in this case, missing data. Now, the cross peaks build up during T1 through a sine function. So when T1 is small, that sine function is going to be small. When T1 is large, the sine function initially grows for quite a while, but of course, relaxation is killing the signal. And that's kind of shown here, in which from right to left, T1, the maximum value of T1 is increasing. And in particular, you can kind of see that initially, as T1 gets longer, for example, in B, the cross peaks look stronger. But then when you go to much larger T1, they're starting to relax away. So part of the game in these kinds of experiments is deciding how large T1 should be. Large enough that the couplings evolve, but not so large that all the signal has decayed away. Here's an example of the dispersive tails coming off the diagonal. And there are various tricks then in processing to try to reduce the dispersive tails by applying so-called window functions or optimization functions to try to truncate the dispersive tails before you kill all of the signal from the cross peaks. So these are what would be called stronger and stronger window functions applied, and you kind of see the effect. This is all part of, I would say, the practice rather than the core theory. Here are line shapes if we have more than 2 spins. Again, these have all been tabulated. There's papers that work out all the various coupling partners. See where we are almost to the end. So that is, skip the double quantum filter cozy for now. Let's see if there's something else I want to say right towards the end. Let's see. Nope, I think that we're in good shape to stop. So we'll take a 5-minute break, and then we can talk about some of the problems from problem set 2. Any questions online before we switch over to problem sets? If not, we'll restart then at 2:30, talk about problems. Unfortunately, I suspect my coffee is totally cold by now.
Actually, that cheaper or not? That's why yeah, like in rare. Not still back. It's starting from Friday, like Friday, you know, no. So after Friday night, like started from 6 to 7, I was excited. But still, arts voices so that it's like it periodically reading it like sorry, food, bad food, like it's so I feel like you're getting just white rice, only white rice. Okay, that's almost just kisses. I think I need to make sure that absolutely. Kimchi is too. I mean, too. So honestly, you do here. Fine. Fine. Oh. Sorry. Oh. Yes. Yes. Yeah, right there. Orange until
Why didn't you learn it? I don't know, I mean,
because he has meeting it and now it is not group meeting, it is kind of like not research meeting. It is not research meeting because he became like associate dean of our graduate school education. So he wants to make it official, like how we need to manage our time, like conversate, discuss how we manage our money. Money? Yeah. Okay. Funding is good. Why? What is that like funding? Yeah, I think it's kind of like administration meeting that actually wants to make sure that people don't waste like money or time. Let's be efficient. Yeah.
basically, he's gonna have a lot less time to do with us, so he has to be proactive.
And also, if Hash, so I think Hash does. I am. But it's okay. But there's no bad thing right now. It's the fact. Right? And and yeah, this will be uploaded to YouTube. So every conversation will upload it to YouTube.
So we're gonna do some problems. Um, you should go through the notes on the cozy and make sure you can do it yourself. Because if you go through the cozy, get the same results, identify the signs of and line shapes, etc. Analyzing other sequences is more or less more of the same. So all the main ideas are there, basically. So is there a particular problem from problem set 2 people want to talk about?
Actually, from the beginning.
Pardon?
From the beginning.
From the beginning?
I would like question 4, which is like the nosy, I think, nosy or NC. Coherence transfer pathway. Question 4.
Now we haven't talked about coherence order yet, so why don't we save that for
Okay.
after next class?
Could you talk about question 9? It's like the pulse that will transform
Yeah.
something into something else.
Oh, good, that's my favorite one.
There are 2 in that I couldn't think of a single pulse to.
Yes, so let's do the easy ones first. So for example, what takes Ix to minus Ix?
Ix to minus Ix.
Mhm.
180 by pulse.
C first.
Pulse along C.
Yeah.
So pulse along Y.
Yeah. Y. Yeah.
Right, so Y will take X to minus X. What about minus Y? Also works. Okay, that's the easiest one. When these pulses, when the operators are all I, like I1, I2, then I mean that the pulse will be non-selective. Whereas if it's I and S, the pulse could be selective for one or the other. So 2IY and 2I1Y, I2Z going to minus 2I1Z, I2Y. So if I can remember that long enough to write it forward. This problem, by the way, is stolen from Christian Griesinger. What was number 2? 2
To I1, I1, Y, Y.
I2 Z going to minus 2 I1Z, I2Y.
90° X.
There's a vote for 90° X. So we draw a picture. A 90° X will take 90° X will take Y a minus Y or Y to Z.
Fingers are on Y.
Yeah. So it'll take Y to Z and it takes Z to minus Y. What about a minus X pulse? So that's right. What about a 90° with minus X phase? So minus X phase will take Y to minus Z and Z to Y,
Same.
so it also works. Either one. Actually, the very first pulse sequence that I thought I invented made a mistake about like that I thought that changing the phase of a 90-degree X pulse, a minus X would change the sign of the result here. And I had pages of these operators written down for this pulse sequence. And I took them to my boss, Peter Wright, and he said, looked at all these pages and said, let's go talk to Mark Rance. And we went into Mark's office and Mark looked at this, for like 30 seconds and said, this will never work. And I kind of slunk out of his office embarrassed. I should take that problem out of the problem set because it always reminds me of that. Okay, then we have 2I1X goes to 2I1X, I2Y going to minus I1X, I2Y.
183. About 83.
A 180 around any axis.
And then X, Y, minus X, Y, all of them.
A 180Y leaves the Y's alone but turns X to minus X. Or a 180X leaves the X's alone but changes Y to minus Y. How about up at the top? I alpha to I beta.
Again, I have 180 pulse. So, any of them.
Any 180?
I alpha is half of identity plus I C.
Mm-hmm.
And I beta is half of identity minus I C. So I just need to flip I C.
So IZ. So any 180 changes alpha to beta, or vice versa. Then we come to one, let's see. How about down at the bottom of the first column, I1 plus I2Z going to I1 minus I2Z.
X plus right. Minus
We have 180 along Y or minus Y.
Does it work for both?
As far as I can see.
Okay, well, let's work it out. So it's I1 plus I2Z. So here, I1 plus I2Z. We want to take it to the what?
I1 minus I2.
I1 minus
Yes.
I2Z.
Yes. 2.
So unless you want to memorize complicated formulas, which you could work out and write down, we can write this right as 2 IX plus IY I2Z
You don't have the leading to.
Yeah. it's-
Oh, and that's not gonna make any difference. And this is equal to IX, I1X, I2Z plus I1Y, I2Z. And we want to turn this into 1 over I want to turn this into I1X, I2Z minus I1Y, I2Z. So a Y pulse by 180 will flip both of these. So we'll get a -1 times a -1, or -1 times -1. And a Y pulse here does nothing to the Y spin and inverts the Z spin. So it looks like, as suggested, a 180 of either plus or minus Y will work. So the tricky ones are something like this one. Right, that's one of them.
Yeah, I couldn't figure this out.
And the trick here is there's no pulse that will do that transformation perfectly. So now we have a pulse of some rotation angle beta and some phase. And what we want to know is what's beta and what's the phase that transforms as much as possible to the desired operator. And then if we were doing it in a real pulse sequence, we would then figure out by phase cycling or something else how to get rid of the other pieces that weren't the desired operator. And here we're just doing it for a single pulse, but there's a long history. If you think instead of a single pulse, multiple pulses and delays, there's a long history and probably super elegant work by Stefan Glasser on what's the maximum coherence you can transfer between two arbitrary operators. Because obviously you would love to know those sequences. So what do you think we should do? If we know how to do this one, we know pretty much everything there is to know about pulses. So what should we do about the phase? Let's think about that first. When we have an arbitrary phase, right, we can always transform around Z to bring that phase to be an X phase, right? And then undo it at the end. So if we imagine that we have I minus and I plus, and we want to apply this phase, the first thing we could do is rotate both of these operators around Z by -5. And that means you just have to apply an X phase beta pulse to those operators. And if we rotate these operators by -5 around Z, we're either going to get plus I phi or minus I phi, right? Depending on how this all works out. And since I can never remember this, we can just do this by hand. So Ix, if we rotate around Z by -5, becomes Ix cosine phi minus Iy sine phi, and Iy becomes Iy cosine phi plus Ix sine phi. So I minus becomes Ix
Cosine
cosine phi
phi.
plus I sine phi. I'll have to multiply this by I.
Yeah.
Right,
Right.
and then,
But you carry a minus sign because
Yeah,
I
minus I sine phi.
I minus is Ix minus I.
Yeah.
thank you. Well, that becomes a minus.
Minus I sine phi.
So, and then minus Iy cosine phi there's
I sine phi.
well, I minus is going to evolve is e to the minus I phi
I minus.
I minus. So then I have I1 minus I2 minus e to the minus I2 phi. And I now can apply a beta X pulse. But at the end, I'm going to have to undo that rotation. So when I undo the rotation over here, the rotation around Z doesn't do anything here. And I'm going to rotate in the other direction here. So now my final operator is E I1 minus I2 Z e to the I phi. The effect of undoing the first rotation to come back to the original frame.
Wouldn't it be e to the minus I phi?
Well, I'm rotating I minus again, but I have to rotate it in the plus direction rather than the minus direction. So here we're rotating by -5 and we got minus I phi.
Yeah.
So when I rotate in the positive direction, I'm going to get plus I phi.
So which is the starting operator and the final operator in this situation?
Pardon?
When do I start and when do I end? Or goes
Oh, this is the final operator.
okay.
And when I'm in this X frame, I'm going to get the result for rotation in X. And then I have to undo the first rotation to get back to my original frame.
And so -5, beta x, and then +5.
Right? I could treat this as a rotation around X of -5, rotation around Z, around X by beta, and then around Z by 5. Because I have, my pulse is being applied with some angle 5. So first I rotate everything to this axis and then rotate everything back at the end. So now now I just need to, since both of these are minuses, I just need to work out what happens when I apply a beta X pulse to I minus. So again, I have Ix minus IIY. Beta X is Ix. Nothing happens. Minus I cosine beta. And then X takes Y to minus Z. So minus IZ sine beta. So up here, that means that
Minus IY
so plus.
plus, yeah. And the I minus is Ix minus IIY. So after X first for the beta angle beta, then it goes to, so it started from minus, so minus IY goes to minus IZ.
Yes.
Under an X pulse.
Yeah. So
So we have
minus
a
minus
plus
is plus.
IIZ.
Sine beta.
So minus IY goes to minus Z, minus Y goes to minus Z. So if I just treat that minus Y as the,
Oh, yes, I was right the first time.
I will,
if you're applying the minus twice, which is what you shouldn't do, that minus Y goes to minus Z, treat that minus Y as sitting inside the bracket.
sorry.
Uh-huh. And now
Super minus. Sorry.
IX is I plus I minus, and minus I plus minus I minus cosine beta minus IZ sine beta. So this is
Or I think that's Ix is I plus plus I minus over 2.
a long day. Minus I minus 1 over 2I. That better?
Yeah, and then I will, I think, cancel with the I in the I from the,
And then, oh, we have an I here. So
Yeah.
this I cancels. So this is 1/2 of I plus 1 minus cosine beta and then plus a half I minus 1 plus cosine beta, and then minus I z sine beta. And all I care about is how much I got to be I1 minus I2z. So make some space here. So I start with I1 minus, and I want to end up with I1 minus, and that's going to be 1/2 I1 minus 1 plus cosine beta. I just picked out the part I wanted. And then I2 minus, I'm only going to pick out the part that depends on z. So I'm going to end up here a minus I2z sine beta e to the I phi over here. And this whole thing should have had and then e to the minus I2 phi. That came from here. And now I see we have 1/2 I minus I2z. Actually, I'm going to put the half over here. Then we have minus I over 2 e to the minus I phi sine beta 1 plus cosine beta. If I did everything correctly. So first, we should get rid of the complex things. So we have I e to the minus I phi, but I is e to the I pi over 2, e to the minus I phi. So what should we pick phi to be? Pi over 2, and then we cancel the phase factor. The phase factors become 1. E to the 0 is 1. So that means I need a y pulse, right? Pi over 2 is a y pulse. So first thing I figure out is phi is pi over 2. And that then reduces this to minus 1/2 sine beta cosine beta plus 1 I minus I2z. And now the problem is simple, right? I just want to maximize that. How do I maximize that? Right, I just use calculus. I differentiate, set the derivative equal to 0, solve for beta. I may not be able to solve exactly for beta. I may have to, at that point, do something numerical, but we see what to do. So we use the phase of the pulse. Here's the critical part, is we use the phase of the pulse to cancel any phase factor that came up in the course of the pulses. And then we use calculus to optimize the flip angle. And I got, what did I get? Every time I do this problem, I have to admit I get something different. I ended up with beta equals 60. The end of the day. I also didn't get phase Y in my notes, but I'll double check that.
Because I'm a little confused. Are you saying that this RZ through phi operation should lead this into this?
Back to the original frame.
Yeah, so when I apply RZ through phi on this operator, I should get here.
In our, it would be better to say at this point, we're gonna end up with some operator A. And then I want to adjust this to get back to that operator. So I start here with the operator I
One minus.
I two minus.
Right.
And after I applied this, I ended up with,
I one minus.
Yeah,
I ended up with
Yes.
this.
Yes.
And then I applied the rotation,
And
and
then
I ended up with, after I dropped the terms that I didn't want, I ended up with basically with this.
Yes.
And then I applied this to this operator,
Oh, yeah. Okay.
and then got this extra factor of I5
That comes
because
from-
this rotated
Okay, yeah.
and the Z didn't rotate.
Yeah.
Of course, there are now a bunch of other terms. You can see that I have 3 terms here. So if I did the full thing, there's going to be 9 terms. But I just picked out the one term that the problem asked about and tried to maximize. It could be in a different problem that wouldn't be what you wanted. In this particular case, we might hope that I can suppress all of those other 9 terms. Maybe some of them are very small. The trig the trig factors turn out to be very small, so I don't care about them. Some of them maybe I phase cycle out. I change from Y to minus Y, see what happens to some things, then subtract out. But it could be that I'm left, say, when I maximize beta, that I could end up with some other operator that's large that is going to be an artifact in the spectrum. So it could be in some cases, my goal would be not to maximize this operator, but to minimize some other operator that I can't otherwise get rid of. And that actually was one of my more cited papers as a postdoc, that in a methyl group, when you're doing NMR sequences, you get lots of terms because of all of the proton-carbon interactions. And I realized after pages of trigonometry that I could never maximize the term I wanted, but the biggest artifact term could be made equal to 0 by picking a particular value. In that case, it was couplings, not pulses, but picking a particular value of T didn't give you the most of the operator you wanted, but it nulled the one you couldn't get rid of in any other way. So here it's it's just a problem, but these things come up in real world, or have come up in real world applications. Anyhow, if you can work through this on your own, you pretty much know everything there is about pulses. And this is the idea. We have this sandwich, rotate everything back to X. That introduces a phase here. Apply the pulse. for that, we don't want to memorize these complicated results. We have to, switch to Cartesians, operators, apply the pulse, and then undo the initial rotation. And then we'll see, in many cases, we can adjust the phase of the pulse to cancel the phase that came up as a result of the evolution. You also see here something that's also always the case. These raising and lowering operators are particularly convenient when you rotate around Z, because you just pick up a phase factor, and the only ambiguity is whether it's negative or positive phase factor. But they're much more complicated when you have to apply a pulse. And the Cartesian operators are much simpler when you have to apply a pulse, and more complicated when you have to evolve around Z. So sometimes in analyses, people are switching back and forth between the two representations in order to understand or make the calculation as simple as possible. And there's one other problem that's like that.
Yeah.
So I can leave you to try that one. The phase for this one, if you think for a while, you might be able to figure out what the phase is without going through the whole calculation we just did to find the phase. But then again, you'll end up having to figure out what beta is by generating some trig terms and then doing calculus. But one of the tricks, and this comes up all the time as we analyze pulse sequences here. Here I recognize that I only needed one of the 9 terms, and I ignored the others. And you've already seen as we evolve these operators under scalar coupling and chemical shift, right? They keep 1 turns into 2, turns into 4, turns into 8 in complicated sequences. Before long, you have 10 pages of trigonometry to deal with. And part of the trick is to have an idea of which of these, at some point, once you recognize that a given operator isn't going to eventually become observable during T2, you can drop it and forget about it for the rest of the calculation. So part of the game of getting experience is in knowing when you can prune to make your life easier. Of course, sometimes, you prune, you get the main signal, and then you see there's artifacts in the spectra. And that means that some operator that you thought was never going to turn into observable signal turned into observable signal because, pulses aren't exactly 180-degree pulses, etc. Then you have to try to figure out which term is it that gives the artifact. But just if you're reading, a paper and somebody presents a pulse sequence and you want to work out how the pulse sequence works, pruning is an important part of simplifying your life. So and see what other one in here is particularly fun to do right now. Here are ones. So problem 5. When you're trying to figure out the coupling pattern, the easiest way, in my view, to do this is to order the couplings from smallest to largest. And first do the large coupling and then do the small coupling and work your way down. So here we have 3 spins and 2 couplings. And in this case, the I1S coupling is bigger than the I1R. And the first thing we're asked about, what's the multiplet pattern for IX? So in the absence of coupling, we would just have a single line at omega x. And now big coupling splits this into a doublet. We're starting with I x. And I know that this is an in-phase doublet because the S operator is the identity operator. And then so this splitting is JIS. And then the next coupling is also an in-phase multiplet because I have the identity operator. And that splits each of these into a doublet split by JIR. So I have a doublet of in-phase doublets, in-phase doublet of in-phase doublets. And because I started with the large coupling, I don't have the problem of figuring out which lines cross each other, which can be confusing. Now, each of these lines I can label with the state of the S and R, right? So this line is I is alpha, R is alpha, S is alpha, R is beta. Here, beta alpha, beta beta. So the four lines, each one is associated with what the spin states of the partners are. So here I start the same, but now this is antiphase. But the R spin is the identity operator. So each of these gets splits into an in-phase doublet. And I get a pattern like that. What would happen if the two couplings were identical?
So either one will be cancelled.
The middle one gets canceled. And that can come up and confuse you because you think you have a doublet, one doublet, and instead you have this antiphase doublet of doublets. And so on and so forth through the rest of this problem. But the main trick, I think, is always start with the biggest coupling. And then you can't get confused about which state is which. The last problem, let me see. Problem 11 is a really important problem because the four A, B, C, D are basically building blocks that are just repeated over and over again in NMR spectra. I mean, NMR pulse sequences. So we want to know both what happens in the evolution through these four different sequences, so that when you're looking at a complicated pulse sequence, if you can reduce it to blocks where you already know the answer, your life is a whole lot simpler.
We can see only three.
Pardon?
We can see only three.
Uh,
ABC.
the fourth one would just be a 90-degree pulse followed by two tau.
Oh, okay.
And that one we already know, right? For that, you get evolution of chemical shift and evolution of J coupling. So that's the fourth one. Now we know. And here are the three possibilities. The 180 is on the I spin. The 180 is on both spins, or the 180 is on the S spin. And then we want to see what the consequences are. You want to try one of them, or you want to just wait for next time? Or are there other questions on the problem set you want to talk about today before we pull?
So in 11,
Uh-huh.
as long as there is a 180 pulse on I, in the middle of that period, I can ignore chemical shift evolution.
We've already worked out, right, that the spin echo
Yeah.
will, on the transverse spin, will refocus chemical shift. So since you already know that, you don't have to do that again.
Yeah.
And you can worry about then what happens to the other interaction. Now, so 4 you can do after tomorrow's class. And
Also 10, will we discuss exocycle?
oh yeah, 10, by the way, the problem is written, it's too complicated. You should ignore scalar coupling for 10. Otherwise, you'll be doing it forever and ever. So we have basically a spin echo that's misset a little bit.
Yeah.
The 180 isn't perfect, and they never are. So if you have so exercycle changes the phase of phi in 90-degree steps. So you're going to do 4 experiments in which phi is x, y minus x minus y, and then try to figure out how you should add or subtract those 4 signals in order to get as clean a spectrum as possible. Exercycle meant something extraordinary, something or other long ago. So here, right, you'd always be starting with IY, minus IY, and minus IY, cosine, omega, tau, plus I x sine omega tau. And suppose the first pulse was an x phase, then this becomes minus I cosine omega tau cosine alpha. And x phase minus Iy to minus Iz. And does nothing to Ix. Then we have to evolve under tau again, and we can collect up some terms, maybe do some trigonometry. And then you can do that over and over again. Of course, this gets to be pretty tedious after a while. So you, of course, could wonder, the extent to which one can make the problem a little easier. And I'm all for doing the calculation 4 times. Actually, only 2. You'll see right away, of course. You can easily see what happens if you change this to minus x, for example. Once you've done it for x, so it's really doing it twice. If we imagine this as an alpha pulse, epsilon pulse of phase 5, and then let's do it the other way. A 180 pulse of phase 5, and then an air pulse of phase 5. In and then I imagine sticking in a 185 and a 180 minus 5 here. And I have this sandwich in which I've applied a 180 Y pulse or minus Y pulse, and then have my evolution, and then a 180 Y pulse. We could work out once and for all what that does. A 180 I now I minus 5 should be a 5. Sorry. 180 minus 5 tau, 180 5. And since we're going to be evolving here, let's think about what happens to I plus and I minus, because that'll be a little simpler, and we can always get the Cartesian operators back. So I minus, right, evolving under tau, we already saw what's going to happen. That's just going to be I minus e to the I omega tau from what we worked out before. That's if nothing happens. So now what happens? I minus, when we apply a 180 of minus 5, is going to be, so I minus, if we apply a 180x, let's say, that's going to become pi x plus iy, which is I plus. And if we applied a 180y, it becomes minus ix minus iy, which is minus I plus. So depending on what we apply here, this is either going to be plus or minus I plus. And then during tau, this is going to become plus or minus I plus e to the minus I omega tau. And then when we apply the next 180, doesn't matter whether it's right, plus x or minus x here. So when we apply the next 180, we're going to get another plus and minus, so these are going to cancel. So the effect, so 185, 180 minus 5, that's obviously an identity operator. So I can stick that in. And now I see that this sandwich, 180 minus 5 tau 185, just reverses the sign of the chemical shift. I'll get it back. Oops. After the second, after this 185, I get back I minus e to the minus I omega tau. The plus minus canceled. The second 180 turned I plus back to I minus. So this sandwich says, it just looks like I've evolved for T, but I've inverted the chemical shifts. So that the pulse sequence now becomes pi over 2 x followed by a 180 I pulse, which is easy for me to work out what happens. And then a minus chemical shift, I could think of as a positive chemical shift, but a negative time, because it's always a product. So then I have negative tau, and then my pulse epsilon I followed by tau. And that calculation is going to be a lot easier to do. You could also see what happens then right away if it was a perfect 180, this wouldn't be here. I just have evolution by minus tau, evolution by tau, no evolution at all of the chemical shift. But it means then, when I see something in a pulse sequence, something like a pi pulse of 5, I can think I move the pi pulse over here and change the sign of tau when doing my calculation. And we'll see in a moment. Here we did it for the chemical shift. What happens to the J coupling playing these tricks? The rules are slightly different, but they'll also be similar rules. So you save tons of time, particularly with 180s. The 90s are harder to deal with. They pretty much have to stay where they are. But the 180s, recognizing when you can move a 180 and pretend that you've inverted time, is a big simplification. So something called sweeping 180-degree pulses. You sweep them all to the edge. So with that, I'll let you work on this and see what happens. Before gradients came in, most of the 180s in the pulse sequence had to be cycled by exercycle in order to reduce artifacts. So if every 180 has to have a 4-step phase cycle, you would look in some homonuclear experiments, and the phase cycle might be 128 steps. Fortunately, sensitivity was terrible, so you needed 128 acquisitions anyhow. But as spectrometers and cryoprobes became so much more sensitive, there was no need for these long phase cycles just to get sensitivity. And then luckily gradients came along. So gradients can do the same thing, as we'll see, in one shot in cleaning up the imperfections from a 180. So now when you look in a pulse sequence, there may still be exercycle on a few critical 180s, but mostly you just have gradients around the 180s, and the phase cycle is very short. And if you're going to 4D and 5D, I mean, you can hardly afford any phase cycling at all on 180s. You just rely almost completely on the 180s to clean them up. That's for next time too. All right, any questions? Yeah.
There's still no gradient coils and MS probes for the most part. So
Right.
it's still doing 128 step
Yes.
cycle with a solid
But your
state.
sensitivity also isn't so good.
That's true.
Any questions online? If not, we'll see you tomorrow. In this problem, if you see, for example, how you take the 4 experiments with the different phases, and then you can figure out how to add or subtract them to give a cleaner signal, then of course you know how phase cycling is.
Yeah.
Because that's exactly how all phase cycling is. It is folded. You can probably tell I love doing these little problems. They're so much fun.